Okay, so we talked in the previous chapter when we talked about optics and light. We talked about interference of waves and interference patterns, you know, the light and dark lines and the bright spots on the wall and all that stuff, which is due to the wave nature of light. And then we talked about the fact that not only is light a wave, but it's a particle. And that it's a particle of energy, and that light carries with it things like momentum, so that light actually can push on things, so it starts to behave more and more like massive particles. You know, before we started entering this realm of quantum mechanics and relativity and other things, light was light and mass was mass. Now we're starting to get a lot of crossover between the two, where light or energy and and things like this start to have these properties like momentum, which were mass things that had to do with mass. And so it shouldn't be too surprising to learn that mass has some of the properties that are kind of like wave-like. You know, like light has a wave-like property, and it turns out that matter has a wave-like property. And you think, well, wave-like properties are kind of strange, right? You have a wave coming in here to hit this wall. These two openings in the wall that are small, you know, kind of compared to the size of the wave. And then you get two waves that are identical that come out of each of these holes. And then as the peaks overlap, you get bright spots. And as the peaks overlap with troughs, with the negative peaks, you get dark spots. And that's what a wave does. But if you were shooting bullets at this, individual massive particles, and the bullets would hit this wall and not go through, and then they would hit this hole and go straight through, and you would expect to just get two places where the bullets hit on the wall, and that's it. And that's true of bullets. It's absolutely true of bullets. But when you get to much, much smaller particles, it's not true anymore. For example, electrons, or protons, or positrons, or other particles such as this. They do not behave that way. They actually, instead of just going through each door and creating two, holes in the other wall or bullet patterns in the back wall, they will actually go through those holes, and then they will create an interference pattern where you get electrons, no electrons, electrons, no electrons, electrons, no electrons, just like with light. And that's an experiment that has been done over and over and over again, which proves that electrons have this wave nature to them. Now, is it light wave nature? No. It has nothing to do with light. And it has nothing to do with a traditional physical wave as we know it, as we understand it. It is a completely different kind of wave. And we call them matter waves, but we also call them probability waves. Usually in physics we call them matter waves because when we talk about things like probability waves, it starts to confuse the heck out of people. But this idea that photons would behave like light waves and like energy particles, and that mass could also behave like particles and also have a wave-like nature. It's called the particle-wave duality. And what that really means is that in certain circumstances, we will want to treat these things like they are waves. In other circumstances, we want to treat them like they're particles. Very rarely are we going to treat them as both at the same time. But they can be treated in either way, but usually under only very certain circumstances, which we are going to define by looking at a little bit of the science and the theory. So, what is the situation in which it is good to treat things like waves, good to treat massive particles like waves? Well, that comes down to what we call the de Broglie wavelength, named after Prince Louis Victor de Broglie. He's a graduate student from France. What a great name to have, Prince, right? Anyway, as he was doing some theoretical work, mostly, manipulating equations that had been discovered and put together by other people, he came across this wavelength that actually calculates the wavelength of photons, which involves the momentum of those photons. But then he said, well, if it involves momentum, of course, we know now that photons have momentum, but so do massive particles. So maybe massive particles can have a wavelength that is associated with their momentum. And it is true that massive particles with any kind of matter involved in them, do have this wavelength, and it is equal to h, which again is Planck's constant, divided by the momentum of the particle. However, remember that h is a very, 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 very small number. And momentum is not necessarily a small number. Okay? Because momentum for a massive particle is the mass times velocity. And for most particles, that mass is pretty big. Most particles that we deal with, like our car, our dog, whatever, those are like massive particles. So if you have a very, very, very tiny number over a big number, because your mass is so big, then all of a sudden you have a fairly small wavelength. Small number over big number equals very small number, right? In order to get a wavelength, and that very, very small wavelength is not going to mean much to us, and we'll talk about that in a second. In order for this to mean something, we really want that wavelength to be about the same size as the particle. Why? Because this wavelength is not a light wavelength, just like I mentioned before. If we're talking about photons, this does come out as a light wavelength. It does come out as a wavelength that demonstrates the length of the waviness of this wave. But if you don't use that momentum, it doesn't. It comes out as what we call a probability wavelength. And what does that probability wavelength mean? Well, a light wave tells you where the energy of the wave is. So where the peak of the wave is, that's where the energy of the that's where the stored energy is in the electromagnetic wave. For a matter wave, where the peak is, the peak of the light wave only tells you where most of the energy is, because it's spread out over the wave. There's bits and pieces of it away from the peak, but most of it is at that peak, and that's fine. Now, for a matter wave, what the wave tells you is it tells you things like where it is, instead of where the mass is. You say, how can that be? Here's a bit of a wave, right? And if this is the peak, you say, well, that's where the mass is, but part of it's over here, and part of it's over here, and part of it's over here, part of it's over here, part of it's over here, part of it's over here. You say, well, where is it? Well, it's actually spread out. It's got this probability of being in different places. The most likely place for it to be is right here. But there is some likelihood that it might be over here, it might be over here. What are you talking about? For most things that have a very, very tiny wavelength, it doesn't matter. Right? So here's me. What's my wavelength? Well, Planck's constant is 6.63 times 10 to the minus 34. I divide that by my momentum. My momentum is like, 100 kilograms, a little bit less, times, however fast I'm moving at the time. That could be, it depends on what you're considering your speed. But consider my speed on the rotating Earth, 1,000 something meters per second or something like this. Some big number. So I've got this 10 to the minus 34 divided by some big number. It ends up being 10 to the minus 38. It's a tiny, tiny wavelength. And so here I am, here's my person, and my wavelength isn't even, I mean, it's not even a measurable part of my width. In other words, where that peak of that wave is inside of me somewhere, but it's so small that I am going to be where I am no matter what. Because that wave never leaves my person. It never goes outside. It never spreads outside of me because it's so small. However, if atom, like let's say a sodium atom, if a sodium atom is moving very, very slowly, maybe 2 meters per second, which is pretty slow for an atom, its de Broglie wavelength ends up being, because the mass of the atom is so much smaller than my mass, it's, you know, the mass of an atom is way down in the 10 to the minus somethings. So if you take a mass of a sodium atom and you divide h by the mass of a sodium atom, time and its velocity, you start to get a wavelength that's about 10 to the minus 9, 10 to the minus 10, which is about the size of that atom. And this is the picture you'll get. You'll get an atom that's like this big and a wave that's like this big. Which means the atom might be here, but it could also be over here, but it could also be over here. And that's kind of like the idea of the electrons in an atom. And the electrons in an atom, they might be here, they might be here, they might be here. They've got this spread of positions that they can be in. And you say, well, which one are they in? You know, they've got to be in one of them. Well, there's no proof that it has to be in one of them. The only thing that we know is this wave of probability of where they might be until we measure them. It starts to get really kind of strange. But the end result is that once you start having this kind of behavior, where the wave, the matter wave, or the probability of where something would be is about the same size of that something, then that something can be in lots of different places at once. It can move from one part of that place, one part of that wave to another instantaneously. It can do all kinds of crazy things. And this is the idea of matter waves. Matter waves are waves of probability that give us information, physical information about particles. They don't give us definite information, they give us a probability of information. And this is one of the reasons a lot of people have a hard time accepting quantum mechanics. They have a hard time accepting quantum mechanics because they say, well, nature is this or that. It's not a probability of things. Well, that's not true at all. That's a lie. Nature is nothing but probabilities. You have, let's talk about the butterfly that's flying over Monterey, California right now. You say, what butterfly? There's a butterfly flying over Monterey, California right now. There's gazillions of them, right? What is the probability that a butterfly is doing this at this location? You can't ask the question without talking about probabilities. Nature is probability. You can't say a butterfly is right here, because as soon as you say that, it's gone somewhere else, right? All things in nature are about probabilities. The probability of a butterfly being right here is something you can say for certain. You can say there is certainly a probability, and I can measure that or calculate it or whatever. But you can never say that you're certain about where something is or what it's doing exactly there. Because as soon as you said that, it's doing something else. And your statement is false. And that is the thing that really people have a hard time grasping, is that all of nature is this way. When you start talking about atoms, you can't say what an atom is doing or what it will be doing exactly, because you don't know until you measure it. You don't know until you actually go and look. And so probability is an inexorable thing. It just is. There's no way to escape it. Well, how do we prove this thing for particles? Well, this is one of the proofs right here. Electrons shooting through a crystal. A crystal is essentially like a big hull of walls with little spots where electrons can go through. And you would expect that the electrons would just go straight through one of those holes and hit something and make the pattern where all those holes are. But that's not what happens. What happens is you get a diffraction pattern. Very similar to when you shine a laser through something that has a bunch of holes in it. Now these holes are in 2 dimensions or 3 dimensions or whatever else, so you get a 3-dimensional, well, you get a 2-dimensional on the screen diffraction pattern instead of just the 1-dimensional one that we get when we just use a laser on 2 slits. But it's still a diffraction pattern, and it still demonstrates that electrons have wave-like properties because they interfere with each other to make these light and dark places, these more probable places where the electrons will be, and these less probable places where the electrons will be. So, let's do some calculations using de Broglie's wavelength equation here. We have an electron that has apparently a measured de Broglie wavelength, or calculated de Broglie wavelength, of 0.167. And you can actually calculate that, or you can measure it. You can measure it by putting it through a crystal, for example, or you can calculate it. But we want to know the electron's velocity if it's non-relativistic, and also the electron's kinetic energy in electron volts. So the momentum is mass times velocity, and all we got to do is plug in the mass of the electron non-relativistic. Remember, if it's relativistic, then you put in a gamma in front of that mv. But if it's not relativistic, you just put in mv. So mv is our momentum. We plug in the mass of the electron in here. We already know what h is, and they've given us the de Broglie wavelength lambda. So we rearrange this to solve for v, and we get 4.36 times 10 to the 6 meters per second, 4 million meters per second. That's not relativistic. It's pretty fast, but it's not relativistic. Part B, electron, to switch it to electron volts, you divide by 1.6 times 10 to the minus 19, because there's 1 electron volt for every 1.6 times 10 to the minus 19 joules, 10 to the minus 19 joules. And what we get when we do that and multiply by the mass of the electron, the velocity squared that we just got, we get 5.4 electron volts of energy. Sorry, 54 electron volts. So what that means is that for an electron to go 6 million meters per second, all you need is 54 volts. You need a 54 volt battery or a 54 volt power supply. That's easy. So you can, with the power right here in the wall socket, you can get to millions of meters per second for an electron. Really fast. And this is actually how electron microscopes work. With an electron microscope, we make focused beams of electrons that come down here. The way that we focus them is we use magnetic lenses, we call them, but they're just essentially coils of wire that create a magnetic field that push and pull the electrons in different directions so that we can focus these electrons. We focus them into these beams that are going straight down through here, and we put a specimen down here. And the specimen, as the electrons hit the specimen, they bounce off of the specimen and interact with each other. They interfere with each other and create interference patterns. And these interference patterns can be made into images. We put it on. We put it onto an electron collector, a detector essentially, and as we detect these interference patterns, we can put it into a computer and show what the image would look like if it was a visual image. It's not a visual image. It's electrons bouncing off of different materials and different shapes of things, creating a diffraction pattern that would look probably a lot more like the diffraction pattern coming directly out of this would look probably a little more like this. You know, some black and white, some bright spots, some dark spots, and some funky diffraction. But with a computer, you can actually figure out, there's some computer modeling you can do to figure out what kind of object made that diffraction pattern, and then you can get an image. And it's not even that hard in most cases. Most cases, the image is pretty close to the diffraction pattern for some of these simpler ones. So anyway, that is the idea of the scanning electron microscope. The scanning electron microscope uses diffraction patterns as they bounce off of the specimen you're looking at. A tunneling, what's called a scanning tunneling electron microscope, actually the electrons go through the specimen and diffract after that. It's like sending the electrons through the crystal. And you actually get a much higher resolution that way. You're able to use you're able to utilize the wavelength of the electron much better that way, and get a much you can take images of something that's much smaller. Okay, so anyway, the reason they call it tunneling is because the electrons, one of the things that electrons have the ability to do with this wavelength is when electrons are going very slowly, and they have to go very slowly for the scanning tunneling electron microscope. When they go very slowly, this wave of the electron becomes much bigger than the electron itself. So it's like having this huge wave of probability where the electron could be, but the electron is only this little tiny thing, like this. So as this electron gets close to something, let's say it gets close to a surface that you want to make an image of in your scanning tunneling microscope, this wave starts to overlap the surface. So here's the surface, and this wave starts to overlap the surface. The electron is therefore capable of being anywhere on either side of the surface. And so it can actually jump through things. We call that tunneling. When electrons' waves start to overlap things that are barriers to them normally. And then the electron actually can jump through something, and it can diffract after that, make a diffraction pattern. And yeah. So here are some actual diffraction patterns, images of diffraction patterns for electrons going through two holes, and electrons and protons. So here's some electrons, here's some protons. If you change the speed of electrons and protons so that you get equal wavelengths, then you get these very similar looking patterns that are equal distances between the centers of the patterns. However, they will not necessarily be the same width of each band is not the same width because the mass has an effect on that. So, here's an interesting thing. This guy named Werner Heisenberg comes along and he says, okay, so, Einstein, you say that light can be a particle, Einstein and Max Born, whoever else did that. And all these other guys now are saying that if light's a particle, it has momentum, then other things that have momentum can have a wave, so mass can have a wave associated with it. So now light can be a particle even though it's a wave, and mass can be a wave even though it's a particle. We've got all these things going on. That's all great. Werner Heisenberg comes along and says, well, if this is true, then all the laws that associated with waves, all the rules that waves obey, matter now has to obey. And one of the laws that waves have to obey is a law that's called the uncertainty principle. So imagine that you're on a wave on the ocean. Okay? We're all on the wave on the ocean. We're getting seasick. And somebody that's on the shore says, how high above the shore are you right now? What's your answer if you're on a wave? I'm not certain, right? What does right now mean? Because you asked me that question, but it took you time to ask the question. And while you're asking the question, I'm going up and down, right? There's uncertainty because of the movement, because of the nature of the wave, right? What if you ask the question, how fast are you going up and down? Same thing, right? It's the same thing because when you're at the top of the wave, you're stopped. When you're at the bottom of the wave, you're stopped. When you're in the middle, your speed's changing all the time, right? And so there's uncertainty. It depends on a lot of things, first of all, but the more you know about one thing, the less you know about the other. For example, if you say, where are you right now? Exactly right, we're sitting here right now at this time stamp, and exactly at 2 o'clock, where are you? And then exactly at 2 o'clock, you can measure exactly where you are. But the only way to measure exactly where you are is to stop the wave at that point. Pretty much, right? You have to go right up to 2 o'clock and stop all the waves and say, this is where I'm at. Right? but you've now stopped the wave. How much do you know about how fast you're moving? Nothing, because you just stopped the dumb wave, right? Or you know less than you would have. And the same thing goes with speed. If you want to know how fast you're going, you can't just measure speed at a single instant. You have to take a place where you were and a place where you are, and take the difference in distance and the distance in time. So it actually takes two places to measure velocity, doesn't it? And so the more you know about how fast you're going, the less you're going to know about where you are. The more you know about where you are, the less you're going to know about how fast you're going. This is a natural consequence and a well-known consequence of wave nature, called the uncertainty principle. And Werner Heisenberg came along and said, if this is true for waterways, and matter has a wave associated with it called a probability wave, it must be true for matter. But again, it's only going to be true for matter when the wave of the matter is about the same size of the matter itself. So only for very small particles that are moving very slowly. It's not going to matter much for bigger particles and things moving fast. It is, but it's exactly where the idea of electrons not really having a place around the atom comes from. And this was a great explanation for that, because they knew that electrons didn't really occupy a particular place around the atom. That was well known. There was no way to prove that they did, first of all, and the behavior of electrons was showing us that electrons don't orbit. First of all, if electrons orbited an atom, they would be constantly radiating light, because all accelerating charges radiate light. Light is energy, which means a constantly orbiting electron would be constantly losing energy, which means its orbit would be getting smaller and smaller, eventually it would collapse and crash into the nucleus, and all matter would be a single point, and we wouldn't exist. And that would have happened a long time ago. So that's one of the reasons that electrons can't be orbiting around. That's the classical reason that electrons can't be orbiting around and around and around. Well, actually, that's the relativistic reason. But the quantum mechanical reason that they can't be orbiting around and around and around and around is because when you look at atoms, they don't have a continuous spectrum of energies. They're not a rainbow, just like we learned it last time. You get these specific energies, which means the electrons go from one energy level or one orbital energy, you could think of it as, to another orbital energy without ever traveling in between, which means they don't orbit, which means they're here or they're here, or they're here or they're here. They're here or they're here, but they're never in between. So yes, that's exactly what it is. They have this ability, they have this nature to them that is uncertain, right? It's a very interesting uncertainty, but it is definitely uncertain. And again, it has everything to do with the fact that they have this wave nature to them. Well, it's large part due to it. So anyway, Werner Heisenberg came along and said this and said, well, one of the most basic uncertainty principles in wave nature is the position momentum uncertainty principle. If you know something, if you know a lot about the position, you'll know less about the momentum. If you know a lot about the momentum, you'll know less about the position, which is the one we just talked about, velocity and position essentially, what they're talking about. But how do you measure that? And he went through and started using the available data, the available experiments, the available theories, and he came up with this idea that this is going to be proportional, this uncertainty. If you multiply how much you do not know about your position, this is your uncertainty in position. So I know where this thing is within 1 meter. This would be 1 meter. And then I know what the momentum of it is within, 50 kilogram meters per second. So that would be your uncertainty there. Multiply those together for atoms and small particles and things moving very slowly. You get, no, it shouldn't be too surprising, but you get Planck's constant, this very, very tiny number. And then, furthermore, it wasn't just proportional to it. It turned out that this product of the two uncertainties always has to be greater than or equal to Heisenberg's, or not Heisenberg's, but greater than or equal to Planck's constant divided by 4 pi. The 4 pi being in there because of the three-dimensional nature of the universe we live in. So what this means is, what this means is that you can actually determine how much you know about one thing if you know how much you know about the other thing, right? I know, so I'm doing this experiment, and I set up this experiment every time, and I run this electron through this experiment, and I measure the position of this electron after every time I do the experiment, and I do it 1,000 times, and I find that my data has this uncertainty in it. You know, I have some electron positions that are here, some that are here, that are kind of, but there's this little spread, and that spread is my delta x for that experiment. And if I know that delta x, then I can use this equation to figure out what the momentum is. It'll be in some kind of range, but I can use this to figure it out. And we just use it as an equation because that gives us the best possible scenario. It gives us the best possible options. But that's what it's useful for. And so here's an example. We have a position electron in an atom is measured to an accuracy of 0.01 nanometers. That's our delta x. The accuracy is how much error you have or how much spread you have. Delta x. So what is the electron's uncertainty in velocity, right? So to calculate that, we plug in our 0.01 in here for delta x, and we solve this thing for delta p, which is our momentum, and then we divide out the mass of the electron. Once we divide out the mass of the electron, we get velocity, because momentum is equal to mass times velocity, and then we get delta v, so we get a change in velocity, or a change in velocity value, say. The delta v is not a change in velocity, it's the spread of velocity. Or it's the error in velocity. So we find that the delta v is 5.79 times 10 to the 6 meters per second. So there's a variation in our experiment of 5 million meters per second, which is not relevant. It's not very much velocity, so not a big deal. So if we want to calculate the kinetic energy for that, we can do that as well. Get 95.5 electron volts. Anyway, sorry, does somebody have a question? Okay, so the really interesting thing is they were having this huge argument about this at a big conference. Einstein and Heisenberg were having a big argument. Einstein at this point is, the rock star of not just the physics world, but he was the rock star really of the scientific world and in many cases just the world. Einstein is a household name today. Everybody knows kind of, something about Einstein, that he was at least brilliant and smart or something. But back then, in the 40s, the 30s, the 40s, the 50s, Einstein was not just a household name because people knew he was a smart guy that lived a while ago, but he was alive at the time and everybody knew a lot more about what he studied. He was always making statements politically, making statements. I mean, he was kind of like, how whenever there's something important that goes on, they have the media goes to Hollywood and they interview some actor that supposedly plays smart parts in movies, and so obviously they must be smart, like Johnny Depp. He's one of my favorites. They'll interview somebody like Johnny Depp and go out there and say, "What do you think of this move that the president has made?" Give some time. I'm not sure if Johnny Depp actually does it, but there are many actors who do, and musicians. That's another great one. Who's that one from Canada that's so obnoxious? Yeah, Justin Bieber. He's always making political statements as if he's some kind of wise person or something. Some 20-year-old punk who has no idea what the world is about. But they're always doing stuff like this. But they did that with Einstein. And with Einstein, it was actually a person who had real brains and experience in the world. And so, but they were doing it all the time. He was a true rock star. And so here you have this up-and-coming guy, Heisenberg, who says, if this is true, then this has to be true. And Einstein, who is the ultimate rock star of the world. Not just the scientific world, but just the world. And they're getting in this argument, head to head, and Einstein's saying, "You're wrong. We can't just willy-nilly assume that the world behaves like a wave just because we think it does, and then start attributing these things to it. That doesn't make sense. There's got to be a better explanation for this." And Einstein finally trying to show up Heisenberg and shut him down for good, he said, "If what you're saying is true, then this also has to be true, because this is another one of those uncertainty principles that has to do with waves. It's called the energy time principle. Essentially, it means that if you know a certain amount about the energy in a system, then you can only know a certain amount about that time when that energy was measured. So there's uncertainty between time and energy in a particular system as well. That's also true of all wave systems. And then after he thought about it for a second, Einstein's sitting there thinking of the statement he just made, and he realized that he had just proved Heisenberg was correct, because there is this in atoms. This does exist, this uncertainty. So it's another type of uncertainty. And here is an example of that uncertainty principle. And it's the same uncertainty principle on the right side, it's just two different things on the left side. So you have an atom that's in an excited state temporarily, storing energy. Okay, so temporarily, there's a time associated with it. That time that it's in that state is 1 times 10 to the minus 10 seconds. And we want to know the minimum certainty of the energy that was in that state, stored in that state. So we go ahead and we use our delta E times delta T is greater than or equal to h over 4 pi. And this h over 4 pi became so important in physics. After a while, they gave it its own name. They called it h bar, h over 4 pi. Anyway, we solved this for the energy because we already know the time. We make that into an equation because we just want to know the minimum. And then, which is the best possible scenario. And you get h over 4 pi. Here's your time that you're plugging. You get 5.3 times 10 to the minus 25 joules. Minimum energy stored in that state for that amount of time. Or 3.3 times 10 to the minus 6 electron volts. So it turns out there's another uncertainty principle there. Not just the position momentum one, but time energy. There are others as well, but we won't get into them. Okay, so particle-wave duality. What does it mean? What it means is that all fundamental waves in nature are going to have a particle nature to them. That was proven with the photon very early on. They were able to show that light comes in these very specific packets of energy depending on their wavelength. And that it has this interaction with matter that is very quantum. They're very quantized. You know, certain wavelengths of light will interact with certain matter because the packages of energy that come in that wavelength fit with that matter, resonate with that matter. Other ones will not react with that matter in the same way. So this particle nature, this packages, the fact that this energy is organized in these packets makes energy particleized. It's not particles of matter or mass, it's particles of energy. It's quantization. For matter, what it means is that matter, even though it's a particle, has wave-like properties. It doesn't mean that matter has a wave associated with like some light wave that travels with it or something. That's not what it means. Even though that is commonly thought to be the case, and even among people who teach this at college levels, unfortunately. It's commonly thought that matter waves, or these waves are some kind of actual physical wave. That's not what they are. What they are is a wave of probability. The probability that something will behave in a certain way is not definite. It's going to do this. It has a spread of possibilities. And until you measure it, it is doing all of those things at once. And if that means your probability is measuring something like position, then that means the electron is everywhere at once until you measure exactly where it is. And yes, that does give rise to the idea of the electron cloud. Why do we talk about an electron cloud around an atom? Because electrons are not any particular place in an atom until you measure where they are. And then it has to choose one of the probable places it can be, and it will be there. The next time you measure that electron in that same exact situation, it will be in another place within the probability. But it'll most likely show up in the most probable place according to its particle weight or its matter weight. And that gives rise to all kinds of crazy things, like particles that interfere with each other because their waves overlap. Particles that can behave like each other because their waves overlap so much. Okay? How many of you have ever heard of a Bose-Einstein condensate? What are the states of matter?
Liquid, solid, gas, and plasma.
Liquid, solid, gas, plasma. What's a plasma?
Superheated gas.
Something that is so energetic that you've actually lost electrons. You've separated electrons from atoms, right? So the electrons and the atoms are not connected anymore, and they can interact with each other because electrons and ions interact with each other in weird ways. And it gets very highly energetic. Fire, lightning, and other things like this, they're all plasmas. Okay? There are more states of matter on the other end of the spectrum. We usually associate this with temperatures, right? Plasmas are the hot things, the solids are the cold things. But if you take a gas and you cool it off without allowing it to liquefy, and cooling it off without allowing it to solidify, and keep cooling it off until it becomes almost absolute zero, which you can only do with certain gases at this point. And those certain gases, you have to cool them using lasers instead of using like a refrigerator or something. You have to use lasers, and you have to use the momentum of photons to slow down the atoms, because slowing down something is the same as cooling it off, right? So what you do is you have this gas, and you slow it down by firing photons on it that are just the right wavelength. In other words, they're just the right size packets of energy to slow down those particular atoms. And you squeeze them until they're in a pretty dense ball of very, very, very slow atoms, about a meter per second. You can get them down to about 0.001 or 0.0001 or 0.00001. I think the coldest temperature is about 10 nanokelvin that you can get them down to. Once you get them so slow, their matter waves start to overlap so much that they become one matter wave. So you might have a million of these atoms, or 1,000 of them maybe, or whatever, just not a huge number, but enough to get something interesting. And they start to get closer and closer and closer together, and their matter waves get bigger and bigger and bigger as they slow down. And they get closer and closer, and their waves get bigger and bigger until their waves are right on top of each other. This is a new state of matter that was actually predicted by Einstein and another guy named Bose. You may have heard of his radios. They are the same guy, actually. But anyway, Einstein and this guy named Bose from India they were, both brilliant scientists of their time, and back in 1930 something, they proposed, as they were studying all this stuff that we're studying now, as they were looking at it, they said, well, if light behaves this way and if atoms behave this way, you can use light to slow down atoms, and then those matter waves we've been talking about will overlap, and all these atoms will behave as one. They will all have the same matter wave, in other words. So it'll be like you have one atom, but they're really 1,000 atoms. And they proposed this idea in the 30s, but they could never accomplish it because they didn't have light that they can control well enough to do that. It wasn't until lasers were invented and really developed really well that we had light that we could control well enough to slow these atoms down. It also required a few other techniques and technologies, but that was the subject of at least 5 Nobel Prizes within your lifetime. This is not new. This is not old stuff. This is new science. The Bose-Einstein condensate, it's called, and that is what is used now to make things like the newest atomic clocks. The newest atomic clocks out there are made by controlling these atoms, slowing them down, so that you get this group of atoms that's very coherent. In other words, they all have the same matter wave. It's like having a laser of atoms, is what it is. A laser of light has all the light shares the same wavelength. That's what lasers are. Well, if you have atoms where all the atoms have the same wavelength, you can actually make an atom laser. And so you can control atoms. Right now we have the ability to manipulate single atoms and be able to tell them exactly what to do, what state to be in, how to interact with another atom. We can move them around one atom at a time. It's incredible the technology we have from understanding this. This is what it comes from, understanding quantum mechanics and developing the techniques and the technology to do it, of course. So let's take a look at another example here using all this stuff together. Here we have a 550 nanometer photon, and it's going to run into a piece of dust that's a microgram of mass in outer space. We want to find the momentum of the photon first, and then how much the dust is going to recoil as it absorbs that light. It's going to absorb all of that energy, we're going to assume. And the dust particle is going to be assumed to be initially at rest. So the photon momentum is momentum equals h over lambda, right? So we plug in our h, which is the really tiny number, the lambda, which is just the wavelength of the light. 1.21 times 10 to the minus 27 kilogram meters per second is the momentum of that photon. Now, conservation of momentum says that the momentums at the beginning have to equal the momentums at the end, all added together and in all three dimensions. So in this case, we're only having two dimensions. So the dust is the before momentum and the after momentum here. Here's our before momentums, our after momentums. Before, the dust particle has a momentum of 0, which is P2. So that one becomes 0. Afterwards, the momentum of the light is going to be 0 because all of its momentum is going to be transferred into the particle and the light will no longer be there. So that would be P1 prime would be equal to 0 at the end. And you get P1 equals P prime 2 equals mass times velocity at this point. So we plug in the momentum we calculated up here, set it equal to the mass times velocity of the dust particle, solve for the velocity, plug in the momentum of the photon and the mass of the particle. You get 1.21 times 10 to the minus 18 meters per second. This tiny little dust particle gets hit by one photon, and do you see any change? No, because that's such a tiny velocity, you're never going to see a change. But since when do you ever get hit by one photon or something? Unless you're in an experiment and they're trying to hit you with one photon. One photon is kind of a hard thing to separate out from all the gazillions of photons around, right? So eventually you can get some velocity out of photons for a dust particle. And that's exactly what pushes the tail of Halley's Comet, is lots and lots of photons. That takes us to the end of this chapter. Next time it's all about atomic physics. So here's an image from a scanning tunneling microscope. Remember that we were looking at scanning electron microscopes, not scanning tunneling electron microscopes. And the scanning electron microscopes could get us down to about I think they got us down to 100 nanometers. You could get us about a tenth of a micron. So that's much smaller than a normal telescope can get you. Normal telescopes will get you to the tens of microns, hundreds of microns. So you can get 100 times or 1,000 times better with a scanning electron microscope. This is scanning tunneling electron microscope. And what you're seeing here, these dots essentially are individual carbon atoms, which is 10 to the minus 10 in size. So that's 100 times smaller still, maybe 1,000 times smaller than a scanning electron microscope. Now we're not actually seeing the atom, we're actually seeing a diffraction pattern around the atom. But still, I mean, that's still pretty impressive. That's a carbon nanotube in case you're wondering. So, cool stuff as we go further into this. Atomic physics, of course, is just one of the branches. It's probably the least, it's probably the most well understood branch for the general public. It's the most understood branch of quantum mechanics. Most talked about because you learn it in chemistry and other things like this. But that's not anywhere near where quantum mechanics ends. And quantum mechanics goes way beyond what chemistry does, way beyond what anybody else does. Way beyond what I mean by way beyond is it goes deeper into matter. It goes smaller and smaller and smaller, the more fundamental particles. So, kind of fundamental. There is a homework assignment posted. So, does anybody have any questions about homework? Because we've got some extra time here. We've got 35 minutes if you have any questions, if you've worked on anything.
Total split for chapter from that.
Yeah, it's 29. What's that? Last night at midnight? Oh, I forgot to set the start time at a reasonable time. Sorry about that. I forget that it has a timer on when it opens. And usually I just like to turn that off, but I often forget. I apologize for that. That's one of the reasons I don't like this system, is because the default is already set. On the other system I use, I could set the default to be open it whenever it's created. And it would just open as soon as I was done making it. So, all right. Here we go.